In this lesson, we're going to be talking about one of the most important skills in not only trigonometry as we move forward, but also throughout all of calculus and beyond. It is a skill that will allow us to convert from one form of a trigonometric expression to another form that's going to be easier to deal with. So this idea is referred to as an identity. Now, we've seen identities before, but we didn't often call them identities at the time. Sometimes we would refer to them as formulas, but identities are essentially an equation. It's just that identities are true no matter what value you plug in for the variable, while equations are only true for particular values of that variable. To see an example, let's take a look at a difference of two squares. We know that x squared minus 9 could be rewritten as x plus 3 times x minus 3 by the difference of two squares formula. So we know that this is true no matter what value of x we plug in, which is why we're able to replace x squared minus 9 with x plus 3 times x minus 3. Now, just to demonstrate why this is true, let's just plug in 4. And realize that 4 squared minus 9, or 16 minus 9, is 7. But I also see that that's the same as 4 plus 3 times 4 minus 3, which is 7 times 1, or also 7. But perhaps you're not convinced that that's actually true for all x, so let's just come up with some other random number like 10. So 10 squared minus 9 is 100 minus 9, or 91. While if we look at the other side and plug in 10, we get 10 plus 3 times 10 minus 3, which is 13 times 7, or 91. 91 is 91. So no matter what value of x you plug in, this is always true, no matter what. But if we take a look at another situation over on the right side, x squared minus 9 equals 9 is an equation. Now we could replace x squared minus 9 with x plus 3 times x minus 3, because x squared minus 9 as an identity is equivalent to x plus 3 times x minus 3. But we should also recognize that this equation, where I set these factors equal to 0, is only true when x equals 3 or when x equals negative 3. These are the only times that this is going to be true. For instance, if I plug in 3 squared minus 9, or 9 minus 9, is in fact 0. So that works. But if I were to take a look at this by plugging in 4, let's say we see 4 squared minus 9 equals 0. 16 minus 9 is 7. 7 does not equal 0. So there's a huge difference between identities and equations. Identities are true no matter what values we plug in for x. I can always replace one side of the identity with the other side of the identity, recognizing that these are always equivalent. And that's much different from looking at equations, which are expected to be solved for x. So today we're going to be looking at fundamental trigonometric identities that are going to allow us to simplify certain types of trigonometric expressions to make them look easier. Now, there are 4 types of trigonometric identities, 3 types of which you've already dealt with before. For instance, the reciprocal identities are ways to convert each of our cosecant theta, secant theta, and cotangent theta into sine, cosine, and tangent, just recognizing that sine of theta is the reciprocal of cosecant of theta, and we have reciprocal identities for the rest of these. Now, this is an identity because no matter what value I plug in for sine theta or cosecant theta or whatever it might be, I'm always going to get the same result. So as an example, if I were to say sine of, let's say, pi over 6, well, sine of pi over 6 is 1/2 by the unit circle. But apparently we're saying that sine of pi over 6 is equivalent to 1 over cosecant of pi over 6. Now cosecant of pi over 6 on its own is 2. So sine of pi over 6 is automatically 1 over 2. So we're just demonstrating that sine of theta is always equivalent to 1 over cosecant of theta. We also learned a couple of other identities. There's only 2 quotient identities here, where we could rewrite tangent of theta in terms of sine and cosine by simply recognizing that it's the y coordinate over the x coordinate, or in other words, sine theta over cosine theta. And for a very similar reason, cotangent of theta is the reciprocal of tangent of theta that we saw back in this point. So that means that cotangent of theta should be the reciprocal of sine theta over cosine theta, which is why it's just cosine theta over sine theta. So this is a way for us to convert, say, tangent of theta into sines and cosines to possibly start canceling it out with other terms that show up in that expression. Now, one of the most common types of identities that shows up are the Pythagorean identities. I'd like to take a look at these Pythagorean identities in a little more detail here, because we saw and we proved this at a prior time at the end of chapter 1, but I want to start off by just manipulating this identity that says that sine squared theta plus cosine squared theta is equal to 1. Now we should know that that's true if we think about the unit circle, because cosine of theta is the x coordinate, sine of theta is the y coordinate, and so if I apply the Pythagorean theorem, knowing that the hypotenuse is 1, we get the Pythagorean identity. But this is not always going to be, for instance, if we see sine squared theta plus cosine squared theta in some expression, then I can automatically replace it with 1. These two quantities, these two expressions are equivalent to each other. So one thing that we can do, though, is we can manipulate this in order to isolate sine squared theta or cosine squared theta separately. Because sometimes we see sine squared theta and we'd like to replace that with some other form. And so we could just subtract the cosine squared theta to the other onto the other side and get the relationship that sine squared theta is 1 minus cosine squared theta. And for a very similar reason, cosine squared theta can be manipulated to become 1 minus sine squared theta. So although this here is the Pythagorean identity, we can actually rewrite the Pythagorean identity in 3 different forms. And we can actually do that in a very similar way to the other identities. So let's talk about those real quick. So even though I know that tangent squared theta plus cotangent, or tangents, I'm going to show the more typical way that I like to write this. So in general, I like to memorize the identity as secant squared theta minus tangent squared theta equals 1. And the only reason I like to do this is because if there are 3 different Pythagorean identities, it helps to memorize them by all equaling them to 1, since 1 was the hypotenuse of our triangle. So if this is one form of our Pythagorean identity, I could start manipulating this by adding tangent squared theta to the other side. And if I do that, that means that secant squared theta is equivalent to 1 plus tangent squared theta. Or the way that it's written in this identity, tangent squared theta plus 1 is secant squared theta. So you really just have to remember one form, because you can manipulate it in order to make it look however you want to. So if I now want to isolate tangent squared theta, then I could simply look to this form here and subtract 1 in order to get 1 to the other side and tangent squared alone. So that would mean that secant squared theta minus 1 is another form for the Pythagorean identity. So now going on to the last one, the last identity that I want to look at is the one involving cosecant and cotangent. So cosecant squared theta minus cotangent squared theta is equal to 1. You can see that this, again, is very similar to the form involving secant and tangent. Notice how there's a minus sign between the terms, still equaling 1. But not only that, instead of saying secant, I see cosecant. And instead of saying tangent as the second term, I see cotangent as the second term. So in a very similar way, I'm going to be able to manipulate this in order to solve for each of the other trig functions, namely cosecant squared theta is equal to 1 plus cotangent squared theta, by simply moving this to the other side. But likewise, if I want to solve for cotangent squared theta, then I can move this to the other side, recognizing that I get cotangent squared theta is the same thing as cosecant squared theta minus 1. So in fact, there are 9 different ways to write all of my Pythagorean identities. But I'd like to realize that the ones that are boxed in orange here are all the forms that are equal to 1, and those are the forms that historically I've memorized. But in the other forms that are in green, I'd like you to realize that every one of them has isolated either sine squared theta, cosine squared theta, secant squared theta, tangent squared theta, cosecant squared theta, or cotangent squared theta. So in other words, anytime you see an exponent of 2 above a trig function, you know that you're going to be able to replace that with some form of a trig or of a Pythagorean identity. Now, the last fundamental identities are referred to as the even-odd identities. Now, these are what are going to allow us to determine how to simplify the trigonometric functions of negative angles. So if we take a look at a few of these, sine of negative theta or tangent of negative theta and so on, we want to be able to look at this diagram or look at the unit circle in order to determine what the values of these are going to be. So the way we're going to start this is by looking at a particular angle from the positive x-axis referred to as theta. Now, one thing that we should recognize about this angle is that by looking at this triangle, this is my x coordinate and this is my y coordinate. But what if we were to look at that same exact angle, theta, except now we look at it going downwards, which is called negative theta. If we look at negative theta, now we should realize that it has a different opposite side. We can see that x is still the same, still got the positive x, only now we got to realize that this has gone downwards, so this is a negative y. So if I take a look at sine of theta, then sine of theta should be, and both of these obviously have a hypotenuse of 1, so let's just make sure to write that in. So my hypotenuse is 1 because I'm on the unit circle here. So if I look at sine of theta, notice that sine of theta is equal to y over x. But if I take a look at sine of negative theta, notice that the sign has changed. It's the negative of y over x. It's the negative of this quantity, which means that I could rewrite sine of negative theta as the negative of sine of theta. So it looks like for sine of theta, I'm able to just pull out that negative. Even if I was to look in a different quadrant, this would also be true. I mean, if we take a look in this form, let's say that we start another way and we look at theta being right here. If this is now theta, then that would mean that this here is negative theta. So by drawing our diagram, we could see again that our triangle would demonstrate that this is y. We would see that going downwards would be negative y. Obviously, our hypotenuse is 1. And now for both of these, it appears that my x coordinate is negative x because I went backwards into the second quadrant. So let's take a look again. If I look at that quadrant, or if I look at that angle, I could see that sine is going to be opposite over hypotenuse. I apologize, I made a mistake on this, didn't I? This was supposed to be y over 1, not y over x. That would have been tangent, okay? So sine of theta is y over 1, so therefore sine of negative theta is the negative of y over 1. Well, now if I take a look over here, sine of theta is still y over 1, okay? But if I now look at sine of negative theta going in the opposite direction, then I see that it's negative y over 1. It doesn't matter what quadrant we're in, this still is satisfied. So since I just made a mistake with it on the last one, we know that tangent of theta, let's look in the first quadrant, so tangent of theta is y over x. So tangent of theta is equal to y over x. So now if we take a look at negative theta, then we can see the tangent of negative theta is again opposite over hypotenuse. In other words, negative y over x. So that implies the tangent of negative theta can be rewritten as the negative of tangent of theta. So it's possible that you're starting to look at these and you're saying, well, that must mean that if I ever see a negative inside of an angle, then I might as well just pull it out front. Well, not so fast. Let's go ahead and take a look at cosine of theta. So if you take a look at cosine of theta is going to be equal to the adjacent over hypotenuse. Or in other words, cosine of theta is obviously just x. But now let's take a look at cosine of negative theta. If I look at cosine of negative theta, notice that the x coordinate didn't change. I'm using the same exact sides. So cosine of negative theta is in fact x. So instead of seeing that these are now opposites of each other, we should recognize that cosine of theta and cosine of negative theta are exactly the same. So cosine of negative theta is actually cosine of theta. Notice I did not pull the negative out to the front. That's because this is referred to as an even function. Just like from algebra, when you evaluate f of negative x and you get the same thing as f of x, that's considered even, while both of these are considered odd functions. And so now that we look at sine, cosine, and tangent, we can refer back to our reciprocal identities in order to find out the rest. We can now see that cosecant of negative theta is the reciprocal of sine of negative theta. So notice that each of those are going to be negative values as well. So notice that the only even functions out of all 6 trig functions are cosine and sine, or cosine and secant. So those are the two where if I ever see a negative angle, I could actually eliminate the negative angle and replace it with its positive counterpart. While for the other 4, sine of negative theta and tangent and cosecant and cotangent, if I ever see a negative angle, I could eliminate the negative angle by turning it into a positive angle and pulling out the negative. So as a recap, we have 4 different types of fundamental identities. The reciprocal identities allow us to turn fractions into non-fractions. The Pythagorean identities allow us to convert quantities that are being squared into other forms. The quotient identities allow us to change sine over cosine or cosine over sine into a single trigonometric function, or vice versa. We could change tangent into this quotient. And the last identities, even odd identities, their sole purpose is purely to be able to change any trigonometric function that has a negative angle into positive angles. So notice that all the rest of these have these just theta involved in the identity, while sometimes we'll see identity or expressions that have negative angles. The first thing we'll do is eliminate those negative angles by turning into their positive thetas and now either pull out the negative or erase it. Now here's an example that we may be faced with in calculus, where we're given kind of a complicated trigonometric function. And by keeping it in the way that it looks, it's going to cause a lot of difficulty in simplifying or solving a particular problem that involves this function. So instead, our goal is to try to simplify this function to an easier form. Now, there's not one set way to simplify or reduce a trigonometric function to an easier form. All you can do is use your trigonometric identities however you see fit in order to make it look different. So for instance, in this one, maybe we start to say, maybe I could use some reciprocal identities. If it appears that maybe using the reciprocal identities could make your life easier, then so be it. Maybe you look at this and you realize that I see a couple of quantities that are being squared. So you think maybe I could use some Pythagorean identities and try to work through it in that way. Or maybe you like to work with sine and cosine. So you decide, I'm going to completely change this into sine and cosine and work from there. There's no set way to do this. All that you're trying to do is use the identities to make this look better. So I'm going to go ahead and use some identities here by turning these into sines and cosines. So let's start by thinking of cosecant squared theta as 1 over sine squared theta. Now, even though that turned it into a fraction, which some may think is a little more challenging, working with sines and cosines is often easier than dealing with all of the other 4 trigonometric functions. So now you look over here and you say, well, I could change cotangent squared theta into 1 over tangent squared theta by, again, using a reciprocal identity. Now, even though that's possible, and I can continue to work with it in the way that it looks, it might be easier for us to change into sines and cosines instead. So instead of changing it into 1 over tangent squared theta, perhaps we chose to use a quotient identity where I could rewrite cotangent theta as cosine theta over sine theta, which means that I now have cosine squared theta over sine squared theta. Now, I agree that this looks worse, but because we see complex fractions now, there may be a way for us to simplify this to make it look a little bit nicer, all right? So let's go ahead and maybe multiply the top and bottom by the common denominator so that it cancels the complex fraction. So I see a denominator of sine squared theta in the numerator and denominator. Okay, so I'm going to go, you know what, I made a mistake here. I wanted to make this a 1 plus cotangent squared theta. I apologize. So I would like to make this as well a 1 plus cotangent squared theta. Now, even if it was minus, there may still be a way for us to simplify it, but it wouldn't necessarily work out the same way that I was going for in this problem. So let's just make sure that we change that plus sign here. Okay, so now we have sine squared theta in the numerator and denominator. Well, if I were to distribute that sine squared theta to both terms in the numerator and both terms in the denominator, this now gives me 1 minus sine squared theta. And on the denominator, I can multiply sine squared theta to both of those terms, and I get sine squared theta plus cosine squared theta. So now it made things look a little bit nicer just because they're in terms of sine and cosine. And I can now replace a couple of these using my Pythagorean identities, recognizing that sine squared theta plus cosine squared theta in the denominator is 1. So I can automatically replace those two terms with the quantity 1. And if I manipulated that Pythagorean identity, noticing that sine squared theta plus cosine squared theta equals 1, then that must mean that 1 minus sine squared theta is the same as cosine squared theta. So I can replace the numerator with cosine squared theta. And of course, cosine squared theta over 1 is cosine squared theta. And I can guarantee that that form of the expression will be much easier to deal with than the original form of that same expression. The fundamental identities, namely our reciprocal identity, a quotient, so this was a reciprocal identity. Here we had a quotient identity. Here individually we had a couple of Pythagorean identities. Using all of those separate identities, we were able to convert this into a single term of cosine squared theta. So this is one way to simplify it. Let's look at another way. Perhaps you noticed that the numerator and denominator both had quantities being squared. And since they were dealing with cosecant and cotangent, perhaps you remembered the identity that said that cosecant squared theta minus cotangent squared theta is equal to 1. So if I were to simplify this in a few different ways, I can manipulate this equation by subtracting 1 and realizing that cosecant squared theta minus 1 is actually cotangent squared theta. And I could also manipulate it so that I see 1 plus cotangent squared theta, which is the denominator. 1 plus cotangent squared theta is the same thing as cosecant squared theta. So perhaps right at the beginning, you noticed that the numerator and the denominator can separately be reduced to cotangent squared theta and cosecant squared theta respectively. So you can rewrite that as cosecant squared theta over cotangent squared theta. Now that already, cotangent squared theta over cosecant squared theta. So this right here already looks easier than what we started with. But I'm going to guess that we could still make it easier. So this might be where I start applying some identities to change into sines and cosines. Okay. So if I rewrite cotangent squared theta as cosine squared theta over sine squared theta, and then I divide that by what cosecant squared theta is in terms of sine and cosine, which with the reciprocal identity is just 1 over sine squared theta. I can now recall by dividing a fraction by another fraction that I can multiply by the reciprocal. So this could become cosine squared theta over sine squared theta times the reciprocal of the denominator, which is sine squared theta over 1. And now because the sine squared thetas cancel out, now we're simply left with cosine squared theta over sine squared theta, or cosine squared theta over 1, which is equal to cosine squared theta. Notice that we get to the same place no matter which way we go, because all I'm using are identities, which are formulas that are true no matter what angle we choose. So no matter what identities we decide to start with, we're always going to end with that same result. So now let's take a look at an example where we can actually use the identities to evaluate particular values of sine theta and all of the other trigonometric identities. Assume we're given information about tangent of theta, which is -5/3. And we're also told that the angle is in the second quadrant. And what we're trying to do now is use the identities to find the rest of these values. Okay, so the starting point here is to recognize that if you're given information about tangent theta, and I want information about secant theta, then I should come up with some sort of identity that relates those two quantities. Now, sometimes there's not a direct link between the two quantities, and so we might have to do some intermediate steps. But in this particular case, we should recognize that secant and tangent show up in one of our Pythagorean identities. I know that there's an identity that says secant squared theta minus tangent squared theta is equal to 1. So that implies that secant squared theta can be rewritten as 1 plus tangent squared theta. So we could go ahead and solve for secant squared theta by just replacing tangent theta with -5/3. So we get that secant squared theta is equal to 1 plus -5/3 squared. In other words, this gives us the secant squared theta. This gives us 25/9, so we need to add that to 1, which is 9/9. And therefore, we find out that secant squared of theta is equal to 34/9. Now, that's not what we want, but it's really close. We wanted secant theta, not secant squared theta. So this is where we have to remember that when taking the square root of two sides in order to eliminate the square, then this gives us that secant of theta is going to be equal to plus or minus the square root of 34/3. But keep in mind, you can't have two different values for one trigonometric function. If I'm given an angle, the answer is either going to be positive or it's going to be negative. And so this is where we go back to the beginning and recognize that theta is in quadrant 2. So since theta is in quadrant 2, then we've got to think about what secant of theta is going to be in quadrant 2. So if you just draw your quick little picture here, I suppose, we could see that in quadrant 2, we remember our acronym ASTC, so that means that sine is positive, and therefore cosine is negative. And if cosine is negative, then so is secant. So therefore, secant of theta must be the negative of the square root of 34/3. Okay, so in other words, secant theta equals negative square root of 34/3. And we found that simply by using our Pythagorean identity. So why don't we go ahead and do the next one here, where we're trying to find what sine of theta is. Now the beauty of this is that not only do we know what tangent theta is, but we also know what secant of theta is going to be. And so if I want to now find sine of theta, maybe we could come up with an identity involving tangent theta and sine of theta. This was quadrant 3. So the identity that involves sine theta and tangent theta, the only one that we can think of, would be that tangent of theta is equal to sine theta over cosine theta. So notice that's the only identity that involves tangent and sine. So if I want to solve for sine theta, I can multiply both sides by cosine, and therefore sine theta is equal to cosine theta times tangent theta. But it doesn't quite help me yet, because even though I'm trying to find what sine theta is, I know tangent theta, but I don't know cosine theta. However, I do know secant theta. So why don't we rewrite cosine theta as 1 over secant theta times tangent theta. And now, since we're trying to find sine of theta, and we know tangent theta, and we know secant theta, then we could plug all the information in and get the value that I need. Well, why don't we convert this directly into one single fraction, and then we can plug in the quantities that we need and simplify. So sine of theta must be equivalent to secant, tan theta over secant theta. And the irony of this is, even though this was our original quotient identity, we actually have created a brand new identity that we didn't know before. We're not expected to memorize this or know this. The point of identities is that once we can solve, or once we can look at one form of an identity, there are many different ways to rewrite that form. And so even though this bottom one doesn't look familiar like one of our identities on our list, it's still an identity because we used fundamental identities to get there. So at this point, we can now just plug in our values and find out that sine of theta is equal to tangent of theta, which is negative 5/3, divided by secant of theta, which is negative square root of 34 over 3. And so if I multiply by the reciprocal, that's going to give negative 5/3 times 3 over the negative square root of 34. And notice the 3's cancel. So we're left with sine of theta is equal to 5 over root 34. And even though that's technically the answer, notice first of all the 3's canceled and we see that the negatives canceled. Okay, and so when we do so, we should be rationalizing the denominator as well. So we multiply by root 34 over root 34, and that's going to give me the final result for sine theta of 5 root 34 over 34. Now notice sine theta is positive, as we expected, because sine is positive in the second quadrant. So now let's take it a step further and find out what cotangent of negative theta is. Now, there's a couple of things to recognize here. We're given information about tangent of theta, but now we're being asked to find information about cotangent of negative theta. So this obviously must require us to use one of our even-odd identities, which allows us to change from a negative angle into a positive angle. So the first thing to recognize is that cotangent of negative theta is equal to the negative of cotangent theta. So now we have an identity that relates theta and theta. So now we just have to figure out how could we come up with an identity that compares tangent with cotangent. And obviously the identity that we would use would be a Pythagorean identity. So that must mean that negative cotangent of theta is the same as the negative of 1 over tangent theta. And so we could replace this now by saying the negative of 1 over tangent of theta, which is negative 5/3. Which, if I multiply by the reciprocal, that obviously becomes 3/5, or the negative of negative 3/5. And therefore, my final result is 3/5. But let's take a look at what this refers to. 3/5 is actually what we found the negative of cotangent theta was. Because we saw that the negative cotangent of theta is equivalent to the negative of 1 over tangent theta. But what we were originally trying to find was cotangent of negative theta. But that's okay, because by our even-odd identity, we can go back again and recognize that negative cotangent of theta is the same as cotangent of negative theta. So cotangent of the negative angle is positive 3/5. So what we've done in 2 of these examples, we've figured out a way to take an expression that looks seemingly complicated, apply some identities, and make it look easier to deal with. While we have another type of problem that allows us to have information, an actual ratio for our trigonometric function, and using that ratio, find other ratios or find other trig functions. And so the starting point is to always determine an identity that relates what's given with what we need. So these fundamental identities are going to continue to pop up through the rest of trigonometry. So really make sure that you're familiar with all of your trigonometric identities, all of your fundamental identities.